So take a look at this problem, and I want you to give it a try first. I would like you to compare water and vegetable oil and decide which one's going to be more viscous. So a few things about these. Vegetable oil is actually a combination of a lot of different molecules. About, for 50% of it is C18H32O2, or many oils. Overall, what we can say about vegetable oil is that it will be nonpolar. It's a very large molecule with very few polar bonds in it, especially compared to water. But what I'd like you to do is to think about this, reflect, and then write your opinion, your answer, as a statement that includes a claim that's supported by evidence, and then that evidence is connected to the claim with scientific reasoning. So this is also a little bit of practice with our scientific writing skills to practice making supporting all of our claims, supporting all of our statements, all of our opinions with some evidence. So I am also going to link on this page a very short 1-minute demo of viscosity of both of these. First, I would like you to list intermolecular forces for each and make an opinion and state your CER style opinion. And then you can watch it and see what you think, how it compares. So pause this video, and then I will share my own version of this. So first I'm going to compare just the intermolecular forces between water and vegetable oil. So water is going to, we've looked at this already, so hopefully it's familiar. I know it's going to have London dispersion forces, and water has a dipole moment, so I know it's polar. It's going to have dipole-dipole interactions as well with itself. It also has these oxygen-hydrogen bonds, and so I know for sure that it's going to have hydrogen bonding interactions as well. Now, it's a neutral molecule, so there aren't any ion dipole interactions. Now, comparing that to vegetable oil, which is this large molecule, I might not have like the exact structure when I'm looking at something like this, but when I see 18 carbons and 32 hydrogens and only 2 oxygens, I know that overall this will be nonpolar. And so I know I'll have London dispersion forces, but I won't have any hydrogen bonding or dipole-dipole interactions. Or if I have dipole-dipole interactions, they're so small that that they're kind of like drowned out by the overall non-polarity of the molecule. And so looking at these and comparing, I'm going to say right off the bat that water has stronger intermolecular forces. And while they have stronger and weaker, I'm also going to note one more piece of information as I compare these. Water is relatively small. It has a molar mass of 18 grams per mole. There's like 3 atoms in it. Whereas that vegetable oil is a large molecule, and so it's going to have a lot more surface area. So I'm going to note that our water is small and our vegetable oil is large, to the point where I can definitely say that that vegetable oil is so much larger that the London dispersion forces of vegetable oil and water, when I compare them, the vegetable oil ones are going to be much stronger. And it won't have any dipole-dipole or hydrogen bonding. So we're not comparing 2 molecules that are the same size, which we've been doing previously when we were like, well, this one will have a higher or lower boiling point or surface tension based on the intermolecular forces. So you can structure your statement about this in one of 2 ways. You can either make the argument that water will be more viscous because it has more different types of intermolecular forces, including hydrogen bonding that's very strong. Or you can make the argument that while water has more intermolecular forces, vegetable oil is such a larger molecule with such a big surface area that it's actually going to have overall stronger interactions between the molecules, and it will be more viscous. So those are kind of the 2 opinions that we can actually have. I'm going to write out my kind of example of a statement for each of those, and then I'll pause while I do that because it'll take a minute. And yours doesn't have to be exactly like this. It could be a little bit different, but it does need to have the same elements that make up a strong argument. It's clearly stating the opinion, and then it's supporting it with your evidence and your reasoning. Okay, so I wrote one statement and then I would like to talk about it and then I'll write another one. It's a little long, sorry. Um, first I took the position that water will be more viscous, and I'd like to break down this statement into the claim, evidence, and reasoning that I'm using to formulate a strong argument. So it says that water will be more viscous than vegetable oil. Okay, so right there, that's the opinion. That's the direct answer to the question of which is more viscous, water or vegetable oil. And I always lead with that, especially in science journals and scientific writing. We don't want to build up to our claim. So usually, when you tell a joke, you kind of build up, and then you have the punchline at the end, and everyone laughs. Scientists are boring. We don't want to build up to a clever punchline. We want the punchline right at the very beginning, very clear, so that way we can skim your paper and not read all the details unless we go, So water will be will be more viscous than vegetable oil because it has stronger intermolecular forces. That right there is my claim or my statement or my opinion. That's what I'm starting with. So now we need to look for the evidence. That should be the next thing that directly supports that first claim that's made. So water molecules are attracted to one another with London dispersion forces, dipole interactions, and hydrogen bonding interactions, while vegetable oil has only London dispersion forces. That was that work we did analyzing the two molecules, right? So this isn't going to be a direct observation because I am formulating opinion from just my base knowledge rather than actually performing an experiment. So this is my evidence right here, how I've analyzed each of the molecules to understand what intermolecular forces exist between the molecules in a pure sample. And I provide that. So I'm saying that water is more viscous because it has all of these other intermolecular forces. But while that's a piece of evidence and it can support my claim, it might not. I have to explain how that supports my claim. I need to do all that interpreting, and it might feel really obvious to me how that supports my claim. But to my reader who maybe has a different opinion, it might not be that obvious. So sometimes our scientific reasoning feels like we're stating the obvious or something that someone should already know. But it's just because we think it already and we already know it. So it feels obvious to us. So continuing this statement. So we've listed our intermolecular forces. And now I'm going to try to tie that evidence and say, my evidence supports my claim because of this reason. And that's scientific reasoning. So hydrogen bonds are typically stronger forces than London dispersion because they arise from permanent dipole interactions between a larger magnitude of partial charge compared to those temporary interactions of London dispersion forces. So right there, what I've done is I've explained why my longer list for water compared to my shorter list for vegetable oil for my different IMFs means that there's more intermolecular forces for water than that. So I have to explain that from the beginning. So this is part of my scientific reasoning, and it explains part of it. So it explains that why I think that the intermolecular forces of water are stronger. That's part of my claim. But I still haven't linked it to why does stronger intermolecular forces mean something's more viscous instead of less? So that's the second sentence. It's the kind of next component of my scientific reasoning. As the strength of intermolecular forces increase, viscosity increases because the cohesive forces between the particles are stronger. So I need to have something in here, and it can look a lot different than this, that explains why more intermolecular forces mean a higher viscosity. And so that's that second piece of my scientific reasoning, because my claim really was two pieces. It was water will be more viscous than oil, and it's because it has stronger intermolecular forces. So I'm going to explain both of those. I'm going to explain how my evidence supports that initial claim. All right, so that's one way you can answer this. Now let's take the argument with a different opinion. Let's look at vegetable oil as being more viscous than water and see how we could write that. All right, I've written now a second statement that makes the argument that vegetable oil is more viscous than water because it has stronger cohesive forces. Polar water molecules interact through London dispersion forces, dipole forces, and hydrogen bonding. Vegetable oil is nonpolar, so only London dispersion forces exist between the molecules. The London dispersion forces are significantly larger in vegetable oil because of it's a much larger molecule. Now, the larger size and the larger London dispersion forces create stronger cohesive forces between the vegetable oil. So in this one, I tried to like write it differently too, so not the exact same like line of argument. And also, anyway, I tried to make it as different as I could. So looking at this though, it still has that same structure that supplies a claim, the opinion, the statement at the very beginning. And it's clear that to my reader that I think the oil is more viscous. And that's the most important part, that your reader knows what your argument is. Now, I'm going to support that with evidence, and I list the intermolecular forces, but it's not clear how that supports my claim right away. So I'm going to highlight this as my evidence. So it's showing a comparison of the intermolecular forces, and the other piece of evidence here is the comparison of the size, so that the London dispersion forces are significantly greater because it is a larger molecule. So my pieces of evidence are, okay, here are all my intermolecular forces, but I'm comparing primarily my London dispersion forces based on the actual size of the molecule. So that's the evidence I'm supplying. And I'm tying it then to my claim by saying it's that size and the London dispersion forces being stronger that create stronger cohesive forces, to link those together. Now, this doesn't feel as strong because when I'm listing so many intermolecular forces, it's like, well, but what about the hydrogen bonding? How do we know it's going to be less of an interaction than the London dispersion? But I could say that about the other one too. So for both of these statements, the way they become stronger is by observational evidence, or something that I can record and measure. And so observations or recorded data from an experiment is going to be a well-conducted experiment, is going to be stronger evidence than an analysis of just the structures that I'm doing here based on these kind of conceptual principles. So let's look at a quick video of this. Let's see what happens. Let's look at a quick 1-minute demonstration of vegetable oil and water viscosity. Here's a demo video that I hope comes through Zoom, but I have a link as well. And what we have is a blue marble in oil, that's what he's holding now, and a green marble that's in water in these capped cylinders. And so we're going to see viscosity by how quickly the marble can travel through the liquid when it's turned upside down. And so that's going to tell us it's more viscous if it goes slower, and it'll be less viscous if it goes faster. And so again, blue marble is vegetable oil, green marble is going to be water. And he's going to now flip these here any minute, and we'll get some observational evidence. There you go. The blue marble took more time. Let's see it again. Yep, the blue marble takes more time to travel through the liquid. And so that means it's more viscous. So that makes our vegetable oil more viscous because that blue marble takes more time to travel through the liquid. Now let's rewrite our CER example. All right, so after watching that demonstration, I can use how the marble behaves as my evidence. So rather than just listing intermolecular forces. And so answering this question then sounds really different if I'm using that video as evidence. So I still have my claim, which is that vegetable oil is more viscous than water. And I'm going to follow that with the evidence that I observed in the video, or maybe this would be something you observed in lab or watched a demonstration. So a marble moving through oil is observed traveling at a slower rate than a marble moving through water. That's my evidence. I saw that marble move slower. That told me that it's actually oil that's more viscous. So, but I still have to link those together. Why does a slow marble tell me anything about the viscosity of oil? And so the next sentence is doing that. The liquid oil is moving at a slower rate around the marble, and viscosity is a measure of how quickly that liquid flows. And so that flow rate is the definition of viscosity. And so that can be my scientific reasoning, and which feels really obvious because it's just the definition of viscosity. And sometimes that's what your scientific reasoning is. Now that we have the London dispersion forces analysis and this demonstration video, there's a more interesting question we can answer than which is more viscous. Or we could answer this in a slightly different way using both. We can say that vegetable oil is more viscous than water, as our evidence from our demonstration. And we can use the intermolecular forces that we compared as evidence to state something like vegetable oil has stronger intermolecular forces than water. Or the London dispersion forces of vegetable oil are overall stronger than the hydrogen bonding interactions of water, right? And then we can support that with we saw the viscosity was greater for vegetable oil through this demonstration. And that tells us that those London dispersion forces, even though those are our weakest interactions, they are occurring for such a large molecule that they are so strong. They're stronger than water's hydrogen bonding. And now a lot of this is also its size, just the larger molecule will move slower than a smaller molecule. So it's kind of both of those pieces. And we can keep going with this and go in more depth, and we'll just stop here because I think now 3 examples of a CER format is what my goal was.